previous video, we talked about the definition of the derivative, which is simply the slope of the tangent lines, which breaks, the slope of the tangent line, not plural, which breaks down to the limit as delta x approaches 0 of the slope of each of the secant lines. And so we have, this is what's called the formal definition of a derivative, or the limit definition of a derivative. In the previous video, we practiced a couple of problems where we used this, so if you're not familiar with that, go back and watch that. But this is a slightly more complicated algebra problem, so we're going to write proper notation. F primed of x is equal to the limit as delta x approaches 0, okay, of f of x plus delta x. Okay, so now let's go ahead and substitute in x plus delta x everywhere there's an x. So notice this is the part that I'm talking about over here in the definition, x plus delta x, and that's going to go right here in just that part. Okay, so this is going to be 6 over x plus delta x plus 2. So it's like I replaced x with x plus delta x minus f of x. F of x is simply 6 over x plus 2. We talked about the need to put parentheses around the f of x. In this case, it actually would not hurt if we didn't, but it never hurts to have extra. All divided by delta x. Now, our goal is to simplify this expression as much as possible. To pull that off, we need a common denominator. Remember, our issue is we need to plug in delta x equals to 0. But if we do that right now, we'll get a 0 in the numerator and a 0 in the denominator, and that doesn't work. So we're trying to find a function that it agrees with this function at all but one point at delta x equals 0. And then, if we get the delta x in the denominator to cancel out, we can simply substitute delta x in. That's the goal anyway. So let's continue to simplify. The limit as delta x approaches 0. Now what am I going to do? I'm going to find a common denominator. You may not want to, but we're got to find a common denominator and combine these fractions together. So I need to multiply the second term by x plus delta x plus 2 in both the numerator and the denominator, and the first term by x plus 2 in both the numerator and the denominator. Now let's see what that gives us. So in the numerator, I'm going to distribute the 6's inside. Be careful, the negative 6 should go there. So I have 6 times x is 6x, and I have 6 times 2 is plus 12. So you see, this is all I did. On the right side, I'm going to distribute the negative 6. So negative 6 times x is negative 6x. Negative 6 times delta x is negative 6 delta x, and negative 6 times 2 is minus 12. Now, that's all over that denominator we found, x plus 2 times x plus delta x plus 2. And now that's all over the big fraction, delta x. So let's see where that takes us. We need to combine like terms in the numerator. So I have 6x minus 6x cancels out, plus 12 minus 12 cancels out. At this point in the numerator, I see that all I have is negative 6 delta x over this x plus 2 times x plus delta x plus 2. It's an ugly denominator that I don't want to multiply out. Y'all, when you find a common denominator to combine fractions together, really the denominator you need to leave factored, unless for some reason there's a, you find to multiply it out, but the goal is to leave it factored. Now remember, this is all divided by delta x. Do you agree that that delta x is really just over 1? So now I could go ahead and flip this fraction and multiply it by 1. The numerator fraction I leave and flip and multiply by the reciprocal. Now, how does that help? It saves space for one thing. I probably would have done that in 2 separate lines if I had more space. But where it helps is I can cancel, let me go back to red, this delta x with this delta x. Now, how is that helping? That's huge because that gets rid of our 0 over 0 issue. So now we're taking the limit as delta x approaches 0 of -6 in the numerator divided by x plus 2 times x plus delta x plus 2. My question to you is it okay to go ahead and substitute delta x in as 0 now? And it is. Okay, so it doesn't give me 0 over 0, so that's going to equal -6 divided by x plus 2. Remember, we're substituting 0 for delta x, not for x. And then that would be x plus 0 plus 2. My computer is, there it goes. Sorry about that, y'all. It just does that sometimes. Okay, so I have -6 over x plus 2 squared. Do you see that? Because this is x plus 2. This is as well when we add the 0 plus 2 together. This is my derivative. That is f prime of x. You know what else it is? It's the slope of the tangent line at x is equal to anything, okay? So that's the slope of the tangent line at x. I probably shouldn't have put the equal to part. Now, what is our x in our problem? I'm going to change colors because we're changing steps here. We have x equals 0 right there. So that's what I'm going to do. I'm going to plug in 0 into my derivative. So I'm finding f primed of 0. That's -6 over 0 plus 2 squared, which gives us -6 over 4, which is -3/2. What have I got there? That is the slope of the tangent line at x equals 0. Now, finally, what did it ask for? It asked for the equation of the tangent line, right? So now I have the slope of the tangent line. That's my m value. Remember, to find the equation of a tangent line, this is almost like step 3. I need y equals mx plus b. I've got the m, that's the -3/2. I don't have the b. How do I find it? Go ahead and plug in 0, 3 for your x and y. So y is 3. That equals to m, which is -3/2. X is 0 plus b. Of course, that's 0, right? So that tells me 3 equals b. The final answer to this problem is y equals -3/2 x plus 3. This is the equation of the tangent line at the point 0, 3 of the function 6 over x plus 2. That's pretty powerful there. As a matter of fact, in the next section it gets even easier. But this is powerful what we just found. Okay, folks, so I thought it worth it for you to see this typed into Desmos. And so I've pulled up desmos.com, where you can just type in a function and get a great looking graph. And remember, the function we looked at is 6 over x plus 2. So I'm going to type in this rectangle in the upper left, y equals 6, and then a fraction bar over x plus 2. I'm just using my keyboard for that. And push enter. And don't ask me why it's not graphing. Maybe it's zoomed way out for whatever reason. There we go. Okay, and you can slide it right over to the center of your screen. These buttons will zoom in and zoom out for you. Remember, we were looking at the point 0, 3, so you can clearly see the point 0, 3 on the graph. I'm going to go to the second line and type in parentheses 0, 3. Close out the parentheses. That'll type a point if you push label. Look at there. So imagine what the slope of the tangent line would look like there. I can't draw it because I can't draw on the Desmos screen, but I would draw it there for you. But you can picture it as a decreasing line just touching that top part of the curve. Now let's graph the line that we found. Our final answer, if you'll remember, was y equals, and the slope was -3/2. So I type in -3 divided by 2, and it puts it in fraction form. Now, I use an arrow to get out of the denominator, and there it is. And remember, we have x, and the y-intercept was 3, so plus 3. And look at there. Is that not awesome? So our red line is our curve, 6 over x plus 2. 0, 3 was the point they wanted our tangent line to go through, and we needed the tangent line at 0, 3. And so the green line is our tangent line. So the slope was negative 3/2. That's what the derivative finds. And then the equation of the line is the green line. Desmos is fabulous, y'all. Use it to check your work. It's wonderful. Now here we have something a little different. It's called the alternate form of the derivative. I was trying to say alternative form of the derivative. I guess that would work too. Use this when c is a known value. So if you're just trying to find the derivative, say f prime of x, but you don't have a place like at x equals negative 3 in this particular problem, you cannot use this alternate form. You must know the c value to pull this off. And the reason is, if you look at this, it says the limit as x approaches c. If you don't know what that value is, you cannot take the limit as x approaches. You always have to have a known value for your limit value. But notice how it really is the slope again. So f of x minus f of c, in other words, two different y values over the x values associated with those y values, x minus c. So that shouldn't be a surprise. Now think about what's happening. It says as x approaches c. So as this x value gets closer and closer to the known c value, and that's basically what we did when we found the slope of those secant lines, trying to find the tangent line, we got closer and closer to x. That's what's happening. Now, these things work, this definition works really well when you have absolute value functions. So I have an example here of an absolute value function for you. Let's see if we can find this limit using the alternate form. Now, I'm noticing a typo right here. I always notice them when I'm in the middle of doing work. That should be f primed of x equals the limit as x goes to c of f of x minus f of c over x minus c. Surely it's not f of x, right? That's the derivative. All right. So let's go. F primed of x is equal to the limit as x approaches our c value as negative 3. So as x approaches negative 3 of f of x. So let's write f of x down. That's going to be the absolute value of x plus 3 minus f of c. So that's going to be the absolute value of negative 3 plus 3. You agree? We're just supposed to, that's what f of c is. That means just plug in your c value, which is negative 3. All right? All over x minus negative 3. Of course, then the next thing we always do is simplify. So f prime of x, or the derivative, is equal to the limit as x approaches negative 3 of the absolute value of x plus 3. Now, we're minusing. Well, negative 3 plus 3 is 0. The absolute value of 0 is 0. So that's just 0 right there, right? And in the denominator, we have x plus 3. Wow, this ought to be familiar. Can we substitute negative 3 directly in? Well, you can sure try, but you know what? When you do, you get 0 over 0. What is that telling you to do? Big time, it's telling you to simplify this expression. And I know that's not a surprise to you because that's what we have done with every definition of the derivative we have. We have to simplify it because we get 0 over 0. All right, we can do that. Now, do you remember that when you simplify absolute value functions, typically you have to rewrite them as a piecewise function? But that's only if you're taking the limit at that break point where the absolute value is equal to 0, and that is exactly what we're doing. That's why we got 0 over 0. So what happens is this turns into a piecewise function. Now, where are we looking? Well, we're looking where the inside is equal to 0, which is negative 3. So we need to take a look at this function when x is less than negative 3, and we need to take a look at this function when x is greater than negative 3. So what happens when x is equal to negative 3? I don't know. We're not worried about that, right? We're taking a limit. We could care less what happens when it's equal to -3. We're approaching -3 from the left and the right. So let's do it. If x is less than -3, say like, for example, -4, then when I plug that into my function, the absolute value changes the sign, right? So to fix that, what I'm going to do is throw a negative in front of that function, like that. So again, if when you plug in one of these values and the absolute value changes the sign of your result, that means you need a negative in front of the function to get the exact same answer, but without writing the absolute value. On the other hand, when x is greater than -3, say like -2, if we plug in -2 in here, that's positive, so the absolute values are not even needed to get the equivalent answer. So that's what we have. Now, we know the first expression on the top simplifies to -1, and the second expression simplifies to +1. So tell me about the limit then. So the limit as x goes to -3. We really have to split it up. If we take the limit as x approaches -3 from the left, that's the top expression. Okay, and I'm just going to put of f of x just to save us some space. That gives us -1. Actually, it's not of f of x. It's of f prime of x. We try to do it again. Try to ignore that prime. If we take the limit as x goes to -3 from the right, it's not really f prime of x either, is it, y'all? Because that's the answer I'm trying to find is f prime of x. But that would still be true. I don't want to say that's wrong. Okay, of f prime of x. And we go from the right, that's the bottom expression, because the right of -3 is bigger than -3. My answer is +1. So what do we say about the limit value at -3? Well, at -3, it does not exist. Why does it not exist? Because the limit from the left doesn't equal to the limit from the right. Well, what does that mean then? How about there's no derivative at -3? No derivative at all. At -3, there is no derivative. There is no slope of the tangent line. Do you know what this graph looks like? What if I just graph it for you real quick? I could use Desmos and make it look all professional. But you know what? This is a V-shaped graph. You know this from your pre-cal class. This is a V-shaped graph. Move over to the left at -3. There it is. So what's happening at -3? There's a corner. And by the way, heads up, corners are not differentiable. You cannot take the derivative. That's a new word too. Differentiable means you can take the derivative at the particular x value. Hey, corners are not differentiable. And it's because, look at the slope of the tangent line over here is 1. The slope of the tangent line over here is -1, which means there is no nice slope. Like, how would you even draw it at -3 as a corner? It's like an upside down seesaw. Can't be done. Cool problem, don't you think? All right, so I have another problem for you. Find the derivative of f of x equals x to the 1/3, or if you prefer, you can write that as the cubed root of x at x equals 0. So what we're going to do is use that alternative form of a derivative again because we have it. More importantly, we can because we have a c value. So here's what we're going to do. We're going to take the limit as x approaches 0, right? That's my c value. Remember, it's f of x minus f of c. So f of x, we can write it as x to the 1/3 minus f of c, which is going to be 0 to the 1/3, divided by x minus c. Now I'm supposed to continue and simplify, and I guess I should use proper notation too. So I can say f prime of x, I should have wrote it on the first line, is the limit as x approaches 0. Of course, in the numerator, x to the 1/3 minus 0 to the 1/3 is x to the 1/3. X minus 0 is x. Now at this point, if you substituted 0 in directly, you would get 0 over 0. So we know this is a problem that absolutely must be simplified. And you know what? I know you see how to simplify it. Because you have the limit as x approaches 0. It's just x over x. And remember what you do with exponents? You subtract them, right? So this is x to the 1/3 minus what's there. That's a 1, which is 3/3. I went ahead and found a common denominator. I'm going to move up to the right. That gives me f prime of x is equal to the limit as x approaches 0 of x to the negative 2/3. I did 1/3 minus 3/3. Now here's the thing. Negative exponents are weird. They're hard to think about, right? So if you don't have to think about them, don't. Just rewrite it the way it's supposed to be written. That's the limit as x approaches 0 of 1 over x to the 2/3 power. Now, you know what that means? We handled our 0 over 0 issue, didn't we? I don't have 0 over 0 anymore. If I plug in 0, I have 1 over 0. Now, 1 over 0 is undefined. It's not 0 over 0 that means simplifying. It's 1 over 0, which is undefined. You know what that means? That the limit does not exist. I know that doesn't make you feel good. It also means the derivative does not exist. So the derivative does not exist at x is equal to 0. Now, I'm not saying every time you have a cubed root of x, you don't have a derivative. I'm saying every time you're trying to find the derivative of the cubed root of x at x equals 0, you don't have a derivative. There's other places you do. As a matter of fact, what does that graph look like? Y'all know what the cubed root of x looks like. So here's my basic xy axis. I'm going to graph this guy in red. And basically, this is, ooh, that's bad. Let's do that again. I don't know that's going to look any better. But basically, this is kind of what's going on. Where is x equals 0? Right in the middle. Now, here's the thing. It still looks like it has a tangent line. You know why? Now, what's slope when you have 1 over 0? Oh, it's a vertical line. So this guy has got a vertical tangent line, which still means the derivative doesn't exist because you've got a vertical line. Remember, a vertical line has an undefined slope, and derivative is just slope. So that's what we have going on there, an unusual circumstance. A couple of questions I have down here for you. One, you see this, is the function continuous at x equals 0? So I'm talking about the red line. They're both red. I'm sorry, I'm talking about the cubed root of x. Okay? So my tangent line, maybe I shouldn't have made it red. Let's play with color. Maybe I should make my tangent line green. So the red line, the cubed root of x. Boop, now it's the cubed root of x. Is that continuous? Well, sure it is, right? I didn't have to pick up my pen to draw that thing. It's totally continuous. It's defined everywhere. But is it differentiable? No. So it's continuous, yes. Differentiable is no. Because our limit was undefined. We got a d and e for our limit. The limit does not exist, which means the derivative doesn't exist. Now, in this case, the derivative doesn't exist because we got a slope that was undefined, which gives us a vertical tangent line. Now, I've got something to tell you about these two questions next. Okay? So, what this is saying is a function can be continuous and not differentiable. But what about the other way around? All right, so I have a theorem for you here. Theorem 2.1 says if f is differentiable at x equals c, then f is continuous at x equals c. Now, please notice, just as important as what this does not say. It doesn't say the reverse. It doesn't say if f is continuous, then it's differentiable. We already know that's not true, right? I showed you two different functions that were continuous. The absolute value v-shaped function, and it wasn't differentiable at the corner. And then I show you the cube root function that wasn't differentiable where it has that weird little curve to it because it had a vertical tangent line. So continuous does not mean differentiable, but it does the other direction. So if you know your function is differentiable, in other words, you can take the derivative at a particular point, that also means it's continuous at a particular point. And remember when we talked about continuity? It had to meet those three conditions. Now that just got easier. Can you take the derivative? Then you know it's continuous. You don't even have to check those three conditions. So I got a proof for you. Now, to avoid all the sloppy handwriting, I just went ahead and typed this thing up for you. So we're going to look at this step by step. So to do the proof, here's where we're going to start. We're going to show that a function is continuous. We need to know that the limit is x goes to c of f of x equals f of c. Now, if you'll reflect back, you may have trouble remembering this, but when we talk about continuity, there were three conditions we had to meet. Number one is f of x has to be defined at c. In other words, f of c exists. That's probably a better way to write that, okay? Step number two, the limit as x goes to c of f of x must also exist. And third, 1 and 2 have to equal each other. So the limit as x goes to c of f of x must equal f of c. And that's exactly what we're trying to prove here, is number 3. And number 3 is true given number 1 and number 2 are true. So really, when you say number 3, you have to assume the first two things exist. So that's what we're going to try to show. We're going to start in a weird place to do that. So watch this. We're going to begin with just this expression. It's not equal to anything, so it's perfectly okay to say the limit as x goes to c of f of x equals f of c. We're going to start right there. Now remember to do a proof at this point. It's not like you're in an advanced calculus class or anything and you're proving these on your own. What I want you to do is look at these with a critical eye. Make sure every step that I'm doing makes sense. You don't have to know why I'm doing it. Okay, that's always good to know, but you don't have to. But you have to say, yeah, that's true, or no, that doesn't make any sense. Okay, so let's just see if this next step that I do is true. It says we're going to multiply by the unity fraction. Remember, unity fraction is just 1. So is it okay to just take an expression and multiply it by 1? Sure it is, right? X over c times x over c. So all I did was multiply this limit by 1. Now, I could have just put it out front and then distributed. That would have been okay, not distributed, but take it inside. But it's okay just to throw it inside because I'm still taking the same limit, okay? Next line, what are we going to do? I'm going to rewrite it. You see what I did here? All I did was move this x minus c to underneath, and now it's right here. And then the numerator x minus c is still out front. Is that okay to do? Sure it is. You know when you multiply fractions, it's just numerator times numerator, denominator times denominator, and this denominator was 1 down here, and so I'm allowed to do that. So just reorganize is the best way I could describe that. What am I doing next? Okay, I'm going to take a limit of a product. Remember, one of the first rules we learned about taking limits is if you have two separate functions, like we have here, you can take the limit of each of these separately. So the limit as x goes to c of x minus c is equivalent to the limit as x goes to c of f of x minus f of c over x minus c. Now let's talk about what we got going on here for a minute before I even show the next line. This ought to look familiar to you. What is that? That's the alternative form of a derivative, right? Because remember that says the alternative form. If we know what our c is, which we're not dealing with that right now, that's just the definition of f primed of c. Okay? On this side, what could we do there? If we take the limit as x goes to c of x minus c, what would happen if we just substitute c directly in? Can we even do that? Well, sure, x minus c is like a polynomial. That's a continuous function. And we know that c just plugged right into that polynomial is perfectly okay. We have a property that shows it. So let's do that. Look there. So if I plug c directly in, that gives me 0. And we already talked about that is the definition, the alternate definition of a derivative. So that's 0 times f primed of c. And does that look like we're going anywhere where we went a minute ago? Well, let's keep going. Let's see what happens next. Right, over to the right. So that means that the limit as x goes to c of f of x minus f of c is 0. Does it really? Well, sure it does. Remember where we started? We started right here. The limit as x goes to c of f of x minus f of c equals 0. We used some fancy trick to do that, but really all we did was multiply by a unity fraction and use some properties of limits. Now, is that what I need? Well, whenever you have a limit out front of a sum or difference, what could we do? All right, that means the limit as x goes to c of f of x minus the limit as x goes to c of f of c equals 0, right? In other words, I took the limit inside. That's a sum difference rule of limits. We proved that. We know we can do that. Okay? Now, what could I do next? How does that take me to what I have right here? Well, first of all, the limit as x goes to c of f of c. That's a constant, right? F of c is just a number. So that is f of c. Hopefully that's what I wrote next. It is, but I added it over too. So I did 2 steps in one. Like we add that to the other side, but the limit of a constant is itself. And we did it. We proved it, right? It's a strange proof, but we proved that if a function is differentiable, look, it's spelled wrong up there. I fixed it in one spot, but I apologize. I forgot to fix it in another spot. But if we have a differentiable function, okay, and where we use that was right here. When we use the limit as x goes to c of f of x minus f of c over x minus c is f prime to c, that's the fact that we have a differentiable function is where we use that, okay? Then if we have a differentiable function, we can say the limit as x goes to c of f of x equals f of c. It's a neat proof. I just wanted you to see it, but really I want you to realize what we're saying. Function differentiable means it's continuous. We do not have that property the other way. If a function is continuous, it's differentiable. Totally not true. And we did 2 problems where we showed that. I hope this clears up section 2.1 for you. There's a lot in there. There's a lot of algebra. Please let me know if you have any questions whatsoever. And have a great day.